How's it going, everyone? In this video, we will be talking about standard deviation. What standard deviation is, it's a measure of how widespread data points are. So we talked about random variables, and we talked about how we can characterize random variables with their mean value. So we can say we don't know exactly what the next number will be, but it'll be somewhere around the mean value. Well, standard deviation is how widespread the data points are, because two random variables can have approximately the same mean value or even the same mean value, but very different standard deviation. They can be, how widespread they are can be very different. For example, let's say you're looking at hours of sleep. So you're surveying people, what's their typical hours of sleep per night, and you're surveying people how many cups of coffee they have per week. Coffee per week. And let's say the average value is somewhere around 7, okay, for both cases. So say for hours of sleep, people tell you, say 6, 8, 7, 8, 7, 6.5. Okay. And let's say for cups of coffee, people give you the answers 7, 0, 14, 5, 10, and 8. Okay. So let's look at our average values. We'll just put it into Excel, right? So we have 6, 8, 7, 8, 7, 6.5. Okay, so hours of sleep versus cups of coffee per week. Okay, so for hours of sleep, we have 6, 8, 7, 8, 7, 6.5. 6, 8, 7, 8, 7, 6.5. And then for cups of coffee, 7, 0, 14, 5, 10, 8. 7, 0, 14, 5, 10, 8. And let's look at the average, or the mean value. So it's 7.1-ish in this case and 7.3 in this case. So very similar mean values. Let's just bring the number of decimal points down to size. Okay, 7.1 versus 7.3. But if you were to look at these random variables and you don't know what is being measured, that it's hours of sleep or cups of coffee, you just see these numbers, right? 6, 8, 7, 8, 7, 6.5. What do you expect the next value to be? Well, it's probably not going to be a 0, right? It's probably not going to be a 14. You wouldn't expect something like that. When you look at these numbers here, 7, 0, 14, 5, 10, 8, they're all over the place, right? There could be a 2, a 3, there could be 14, there could be 15, there might even be a -1, right? So the mean value is very, very similar. But we can tell that these two sets of data are different. These two random variables are different somehow, even though they're characterized very similar if we look just at the mean value. So what's different about them is how widespread the data points are. What's different is something called standard deviation. And it's a very important measure. Okay, so let's say, for example, there's some medicine. And the medicine says that there's, say, 200 milligrams of the medical ingredient in every pill. Well, the truth is that 200 is an average value. It's not like every single pill has the exact, to the 10th decimal point, the exact number, the amount of that medical ingredient. Okay? That's an average value. But how widespread are those data points? Do you think they range from 100 milligrams to 300 milligrams? Or do you think they range from 199 milligrams to 201? Well, hopefully it's this one here, right? Then the medicine works the way it's expected to work, right? If the range is 100 to 300, well then sometimes the medicine won't work and sometimes people are overdosing, right? So it's not just the mean value that's important. The standard deviation, how widespread the data points are, is also very, very important. Okay? So how do we come up with a measure for how widespread the data points are? Well, it's intuitive to look at the difference between the data points and the mean value. Okay? So in this case, for hours of sleep, and I'm just going to bring this cups of coffee information down here. So for hours of sleep, these are our x values, right? X subscript I. We can take all of our data points and subtract the mean value. Okay? So 6 minus 7.1, and that's negative 1.1, and we can do that for all of the other data points. If you're not sure how I'm doing this in Excel, don't worry, it's just a fancy calculator, right? So for every single data point, we can say, okay, one data point is negative 1.1 from the mean value, right? So it's 1.1 below the mean value. One data point is 0.9 above the mean value. Another data point is negative 0.1 below the mean value, and so on, right? So for every data point, we have how far they are from the mean. Right? That's a good measure of how widespread the data points are. And when we take the average of that, we get 0. Right? Well, that's not very helpful, right? Because how widespread the data points are, it's certainly not 0. They're not all equal to the mean value. And the reason we get 0 here, and we will get 0 every single time if we do the calculation right, is because you're supposed to. Okay, if you're looking at how much the data points deviate from their own mean value, well, the deviations above it and the deviations below it, the differences above it, the differences below it, they should balance each other out and give you 0. That's why the mean value is the mean value. Let's take our cups of coffee and do the exact same thing. Okay, so we just need to change the formula so that we're subtracting the mean value of the cups of coffee, not the mean value of hours of sleep, right? So 7 is 0.3 below 7.3, right? So we look at the differences here between the data points and the mean value, and they are bigger, right? Instead of everything being around 1 or less, right? We have 0.3, 0.7, right, as a difference, negative 0.3, but then we have rather large numbers, negative 7.3, 6.7 above, 2.3 below, 2.7 above. So we can see already these data points are widespread, but when we take the average of those differences, we get 0 again, as we should. It is the mean value because how far the data points stray above it and how far the data points stray below it is equal. And this can be proven mathematically. Now, how do we handle that situation then? How do we ensure that our negatives don't cancel out our positives? Right? Because what we're interested in is just how widespread the data points are, not so much above or below. Right? Well, what we can do is we can square all of these differences. Right? Because when you square a negative, you get a positive number, and when you square a positive, you also get a positive number. Okay? So we can square all of these, and then when we take the average, we're taking the average of a bunch of positive numbers, and we actually get something meaningful. Okay? And we can copy that here to our coffee situation. And we end up with something strange. Okay, so we don't have 0 anymore, so that's good. But look at the value right here for hours of sleep, 0.5. Is that how much the hours deviate here? The mean value plus or minus 0.5? Well, seems like it's a bit small, right? They deviate more than that from 7.1. Right? Look at this value here, 18.6 for cups of coffee. Is that how much the numbers deviate from 7.3 plus or minus 18.6? I mean, 7.3 minus 18.6, that's going to put you in the negative cups of coffee, right? Like people are throwing up cups of coffee per week, right? And if you add it, you have a number above 20, right? We don't even get close to 20 here. Okay, you get a number way above 20, almost 30, right? So what's wrong with this value, right? It's not 0, but there is a problem with it, right? It's too big, right? Or in this case, it's too small. What's happening is because we're squaring these differences, we're not just changing negatives to positive, we're also affecting the magnitude. Okay, the numbers that are below 1 are going to become even smaller, and the numbers that are above 1 are going to become bigger, in some cases significantly bigger, right? So to undo that magnitude change that happens with squaring, we can take the square root. Okay, so let's take that square root. And we'll take the square root here. Right, we're just taking the square root of that final value there. And now we actually get a number that seems like it's quite representative. Okay, so for hours of sleep, standard deviation 0.73. Typical person's hours of sleep, 7.1 plus or minus 0.73. Yeah, that seems pretty reasonable, right? 7.1 minus this value and 7.1 plus 0.73. We get this is a typical range from about 6.5 to 7-8 hours. Yeah, it seems to be where the typical data points are, right? And if we do that calculation for cups of coffee, right? 7.3 minus our standard deviation and 7.3 plus our standard deviation, we get the range from 3 to about 11.5. From 3 to 11.5 cups of coffee a day seems to be like the typical range, right? Not considering some outliers. Yeah, it seems to be reasonable, right? So that's how you calculate the standard deviation. Now in Excel, there's a quicker way of doing it. Okay. You can input stdev dot s or p depending on the situation, and I'll explain the difference between standard deviation with an S or with a P. I'll explain that a little bit later. What we calculated here is actually the standard deviation with a P. So even though technically the correct way would be to calculate it with the S, but I'll get into that later, right? And so we see our long manual way of calculating it gives us the same correct answer. We can do the same thing here, and we see our long manual way of calculating gives us the same answer. So let's write down exactly what we did. Right? The symbol for standard deviation is sigma. It's the lowercase Greek s. Well, we added up a bunch of stuff, but we didn't add up the data points. What we added up was the difference between the data points and the mean value. And well, first we took the average of all of that, and we ended up getting a 0 all the time, as we should. So then we decided, okay, we're going to square this difference so that we're not getting a 0. So we took the average of the squared differences, but then we had a problem with our magnitude. It was too big or too small. So we took the square root of the final result. And that's the formula for standard deviation. That's exactly what we just did. We looked at all of the differences between the mean value and the data points. We squared those differences. We took the average of that, right? We added them all up and divided by the number of data points. And then we took the square root of our answer. That's the formula for standard deviation. And that's why standard deviation is a good measure of how widespread your data points are. Now, when we're working with data, right, there's a difference between the population and the sample. The population is the entire group of units, it could be people or whatever else you're measuring, the entire group of units that you want to make a conclusion about. Usually you don't have access to all of them. Right? Usually you have access only to a subset of them. That subset is called a sample. Right? For example, you want to know the average household income of the entire country, but you can't ask everybody in the entire country. You can only ask 100 people. So the population is the entire population of the country. The sample is the 100 people that you can ask. And because these numbers are different, right? The average value of your study might not be the same as the population mean. We use different symbols for it. Okay? So for population and sample, when we're dealing with the mean value, for the population we use mu, and just to recall the equation for that, add up all of the data points from the first to the last, divide by the number of data points. For the sample, we use the symbol representing our random variable, in this case it's x, with a bar on top. So this is the sample mean. And the equation is the same, right? You add up all of the data points and divide by the number of data points. So for standard deviation, you can also have different values for your population standard deviation and for your sample standard deviation. So population standard deviation, well, we wrote that above. You add up, well, that's supposed to be an n, the squared differences between the data points and the mean value, divide by the number of data points, and take the square root. Okay. For the sample standard deviation, we use a lowercase s, right? Because how widespread the data from the 100 people that you ask could be different than how widespread the data is from the entire population of the country, right? So we use a different symbol, and you add up all of the data points. Well, you add up the differences between the data points and the mean value squared, right? Divide by n minus 1, and then you take the square root. And you might notice, well, hold on, the equation is different. Okay? There's two differences in the equation for sample standard deviation and population standard deviation. In the sample, well, one difference is right here. We're using x bar instead of mu because we're working with a sample. We don't know what the population mean is if we're working with a sample. We only know the sample mean, so that's why we're using x bar instead of mu. But the big difference here is n minus 1 in the bottom instead of n. Okay, so for a long time, people thought that it should be an n in the bottom because you're taking an average, right? It's the average of the squared differences. Right? That's what we did in our Excel form here, right? We took the average value of the squared differences. and then we took the square root of it just to bring it to the right size, right? Oops. And for a long time, people thought, yeah, it should be an n. But they kept getting a bias, right? And in mathematics, a bias means that you're consistently getting a number either too big or too small, and you can actually predict how much bigger, how much smaller you're getting it. So people would be dividing by n, and they would consistently be getting a calculation of sample standard deviation that is regularly smaller than the population standard deviation. Now you expect that the sample standard deviation would not be equal to the population standard deviation necessarily, right? Your sample may behave differently than the population. The 100 people you happen to ask your survey question to might give a response different than the average of the entire country, the entire city, whatever it is you're interested in. So you expect the sample standard deviation to be different than the population standard deviation. But for it to regularly be smaller, well, that tells you that there's a bias at play, right? It's not just different. You're not just guessing a little bit off. You're guessing a little bit off more to the negative side. And what corrects this bias, and there's a mathematical way of showing this, what corrects this bias is turning that n into an n minus 1. So if you use n minus 1 instead of n, then you get a more accurate calculation for sample standard deviation, a less biased result. Now what would cause that bias is because your differences are not looking at the difference between the data points and the population mean. You're looking at the differences between the data points and the sample mean that comes from those very same data points. Well, of course, the data points will be closer to their own average than to the actual real average, whatever that is. That's where that bias comes from. And dividing by n minus 1, that's how you would correct for that bias. So if we were to be correct in our calculation here, if we want to know the average hours of sleep in, say, the city we live in, or the average cups of coffee consumed in the city we live in, and we happen to ask our 5 best friends, we should be calculating the sample standard deviation, right? Because our 5 best friends are not the entire city, right? So a better estimate for the standard deviation in this case is 0.8. And in the case of cups of coffee, a better estimate is 4.72. And you'll notice it's bigger than what we calculated before. Because if you divide by n for a sample standard deviation, you tend to be biased in the negative direction. So that is standard deviation. So hopefully that explains that, and enjoy the rest of the material.